Good morning, Professor Ralf, and hello, everyone. Welcome to the OpenFOAM and the Combustion Simulation webinar. Today we are very happy to have Professor Ralf Deiterding from University of Southampton to give us the webinar. And the title is about adaptive high-resolution simulation of reactive high-speed flows with the AMROC framework. So before the webinar, please allow me to first introduce Professor Deiterding. Professor Ralf Deiterding is professor of numerical methods in fluid dynamics at the University of Southampton. He joined the University of Southampton in 2015 after appointments at the California Institute of Technology, Oak Ridge National Laboratory, and the German Aerospace Center, DLR. After studying techno-mathematics at the Technical University of Gloucester, he obtained a PhD in applied mathematics and computational fluid dynamics from the Brandenburg Technical University, Cottbus, in 2003. His research focuses on the development and application of innovative high-resolution and multi-scale numerical methods for CFD. He is the main author of the simulation frameworks, AMROC, and also virtual test facility. And here we have the link from the flyer, if you would like to have a look. Okay, now I give the time to Professor Ralf. Now the time is yours. Thank you very much.
Okay, thank you for the very comprehensive introduction. So I'll hope that connection will be working fine. So basically when connection is going down, I'll turn off the video. Yes, you have seen the title of this talk. And so what's the motivation here? So in this presentation, I want to explain my source generally that led me to the development of AMROC and what that system is about. So it's a little bit larger than just combustion simulation. And let me start as an introduction with my general thoughts. What's about CFD meshing? So we are living in the third generation of CFD. Yeah, so the first generation of CFD that used to be structured mapped grids. Yeah, and of course it's difficult to automate that. And the idea of AMROC always was to automate many of the procedures. So the second generation would be unstructured meshes. Yeah, unstructured meshes with triangular grids. And then if you want to do fluid structure coupling, yeah, for instance, we have this body that is moving through the domain. And of course, we have mesh stretching. And at some point, you have mesh regeneration. And mesh regeneration naturally is quite a bottleneck in such kind of CFD simulations because unstructured meshing still is basically a globally coupled problem. And nowadays, we live what is called third generation CFD and third generation CFD. So this is about Cartesian grids where you can construct the grids much more locally and you embed the boundaries. So for instance, with level set techniques, but the problem then there is if you do level set techniques, and we'll see this in AMROC extensively, you struggle with incorporating viscous flows, yeah, boundary layers. And so one direction that we want to go with the software, and you'll see some indication in this presentation, is to incorporating boundary layers through type of overset meshes. And the idea here is we have a boundary layer mesh near the body, and then in the background, we have a Cartesian mesh with dynamic mesh adaptation. And this idea nowadays is called strand meshing. And the core idea is that you grow the boundary layer mesh from an unstructured surface mesh. So you basically, you grow it into the normal direction. Okay, so that is the overall idea that I'm pursuing with AMROC. And I'll give you some indication for these various approaches in the talk. So here's the outline. So AMROC originally was an entirely Cartesian and structured system, and we'll see some examples of that, what all has been achieved. Nowadays, we have also extended it to mapped meshes, and we will see both then in this big section that is about combustion simulation. And then we come to a different class of reactive high-speed flows, and this is then hypersonics. And there we have particular dissociation reaction. As a very quick outlook at the end, I'll show you how you can also do with such a system, how you can do quasi-incompressible flows with the Lattice-Boltzmann method. Okay, so the work has been done in collaboration with various people, and here on the slide are only those people who had certain influence on the presentation that I'm giving. So first to name for the combustion bit, of course, Han Peng, my current PhD student, and Shay Atkins for the hypersonics, and there are some results from Pushbender. And then for the Lattice-Boltzmann method, yeah, that was Michael Grondeau and Stephen Wood. And some of the simulation cases are in collaboration with various professors over time. So what was the original AMROC about? Yeah, so the original Cartesian AMROC, first of all, is about solving hyperbolic equations. So here we have a general hyperbolic equation in 2D, hyperbolic conservation law. And then what AMROC is doing, it is implementing structured mesh adaptation. So structured mesh adaptation after Berger and Colella. And in this approach, so it is genuinely unstructured to the flat layer unstructured mesh that you would be knowing in OpenFOAM. So versus organizing the solver based on a single cell element, these solvers are organized based on the block, yeah, a rectangular block on which then the discretization is formulated. And then when we apply the discretization, we do this on a sequence of blocks. So we do a loop over all the blocks. And then the discretization is applied in each local block. But in each local block, you use IJK to implement the discretization as efficient as it is possible. Yeah, and then through hierarchical refinement, we obtain an entire hierarchy. And the point now is that the higher level grids are not embedded into the coarser ones. Yeah, so the entire data structures remain unchanged, that we have big blocks over which we can sweep quickly, taking advantage of caches. And then the hierarchy, they are communicating with prolongation and restriction operation, with interpolation and averaging. So it's a technology genuinely constructed for hyperbolic problems. So we have here the general finite volume formula, and it is an explicit formula. Yeah, so it is bound, that is bound by the CFL condition, and the CFL condition is equally satisfied on all levels of the hierarchy, and this is accomplished by doing time steps on the finer levels. Yeah, so this approach always comes together with hierarchical time stepping. So we are not taking a time step based on the finest level. Yeah, so there is computational advantage on the coarser level by taking larger time steps. In order to construct these blocks, so they are based on the refined cells, but they are then bundled together. And for that, you need a special algorithm, a so-called cluster algorithm from image analysis originally. So I'm not going into the details of that, but these grids have to be specially constructed. So then when we have these grids, they are communicating with ghost cells. Yeah, so here we see two grids on level 1, yeah, based on level 0. Yeah, so and then on each round of these grids, you have a layer of ghost cells. And the ghost cells, they are filled according to the requirements. So if the ghost cells are overlapping with a neighbor, they are filled by synchronization. If they are at the boundary, they are filled by physical boundary condition. Yeah, and then those remaining ones, they have to be filled from the coarser grid by interpolation. Interpolation in space, yeah, which would be typically a linear interpolation, bilinear, to avoid overshoots and undershoots. And then we have interpolation in time, because we do hierarchical time stepping. Once, for all the blocks on a level, you have set the ghost cells, you can then do the sweep over each of the block independent from the other. So at that point, it becomes genuinely parallelizable. An important operation in these overall procedures is, of course, to ensure that this is mathematically entirely consistent. Yeah, so you are getting a situation which would call, because we are using Cartesian grids or structured grids, we are getting a situation that would be in finite element world called a hanging node. Yeah, we would be having something here like a, so to speak, hanging node. But what we have in finite volume world is, of course, we have a coarse cell, and then we have several fine grid fluxes that we have to consider to make this mathematically consistent. So instead of the simple finite volume formula that we saw on the previous slide, we have to implement a finite volume formula that ultimately considers the addition of the fluxes in space, yeah, from the fine cells, and also then the fine fluxes in time. So we have to implement this formula somehow. And in the Berger-Colella method, this formula is implemented through a correction method. So in Berger-Colella, you first update always the respective coarser grids, and only then afterwards you update the finer grids using time interpolation on the boundary. And so what we do is basically we implement this with a so-called correction pass. So you update the coarser grid, you update the correction element by the negative coarse grid flux. Yeah, then you do the loop over the hierarchical time steps, and you add together the fine grid fluxes. And when then those levels have caught up with one another, you apply the correction term. And because we initialize this with a minus on the coarse grid fluxes, yeah, that gets eliminated, and all what we remain with is then the sum of the fine grid fluxes. And like that then, if we are considering the combined view of the grids, looking from on top, like we would flatten it, we have a totally conservative situation. And that, of course, is quite important, yeah, for the mathematical consistency. Now, in order to consider embedded geometries or complicated geometries in AMROC, so we initially implemented level set methodologies. And so in a level set methodology, you use a marker function to indicate where the boundary is. And in our case, it's a signed distance function. Yeah, that is negative on the outside and positive on the inside. And particularly because it's a full distance function, it is differentiable. So you can always compute the normal over the boundary. So, and that distance function could be initialized and constructed analytically, or when we have complicated meshes, we have a special algorithm for that. What you then do is, so let's say this here is our outside of the domain, you use one-sided interpolation extrapolation operation like it is depicted here to construct then actually values for the cells that you use or abuse as ghost cells. Yeah, so you can see here that the stencil has to be adjusted, and you want to avoid a too aggressive extrapolation because when you do shock waves, that can create significant overshoots. And then we would be extrapolating into the ghost cells the density and the pressure. And then the velocity you also extrapolate, but of course you have to flip it. Yeah, to, for instance, to impose a no-slip boundary condition on the boundary, or to impose a slip boundary condition with a certain wall velocity. Yeah, a wall velocity W, that is of course essential for fluid structure coupling. Yeah, so with that, we would have an algorithm then that we can use for fluid structure coupling, and fluid structure coupling then in the VTF is done in a separated approach. So we would be doing a time step on the fluid, we exchange boundary conditions, we do a time step on the solid. Yeah, and that would be here then if we do inviscid boundary conditions where we only communicate the hydrodynamic pressures instead of the whole stresses. So with this embedded boundary technique, you have a very flexible methodology that works particularly well for inviscid flows. Yeah, so here we have a verification validation test, already quite a bit old, but it's a nice validation experiment for these embedded boundary techniques. So basically spheres that are imposed to flow in a shock tube, Mach 10. Yeah, and you see that the agreement using two levels in addition, the agreement between the computational results and the experimental results is quite good. It's a pressure-driven problem, and that works quite nicely. So it's always in the experimental accuracy. And of course, now the point of doing level set methods is we can do heavily moving problems. Yeah, so here we see then a more sophisticated experiment, yeah, where the spheres are actually driven by the shock wave. Yeah, and you see the agreement with the experiment and the simulation is excellent. Yeah, so viscosity doesn't play much of a role, so our Euler solver can reproduce this really nicely. Yeah, it is done with full mesh adaptation. Yeah, and here then on the right, yeah, you see basically the mesh adaptation moving in this case, and the mesh adaptation is done virtually in every time step. Yeah, so that is generally quite different than with OpenFOAM, where you do mesh adaptation only very rarely. Here we would do mesh adaptation basically in every time step to ensure that the moving bodies are always embedded nicely in the finest level. Yeah, so one word about parallelization, how this is generally done in AMROC. Of course, parallelizing these hierarchies is a relatively complicated load balancing problem. And in AMROC is done an approach that is called rigorous domain decomposition. So we would be adding together all the workload from the finer levels and projecting it down to level 0. Yeah, so all the workload from having finer cells and doing hierarchical time steps on them, that is all projected down to level 0, and then the partitioning is done only on level 0. And that is assuming and accepting certain smaller load imbalances, but it is done so that you can save then the communication cost over the parallel machine between the levels, yeah, to have this strict locality. Yeah, so that is the core idea here. So many of the operations then can be formulated completely strictly local, and you don't have to consider communication. Yeah, so we construct a space filling curve then for the partitioning that is common on structured grids. Yeah, it's a space filling curve that goes through in a hierarchical way, in a recursive way through the mesh. And then you can split it up at certain intervals, and that is then load balanced. Yeah, so, and here we see the higher levels and then of course the different amounts of workload. So in the movie that we hopefully can see here, this is again this problem with the spheres, with the static spheres in 2D. And what you see is the different levels, yeah, through the Z dimension, and the colors are the distribution to the processors. Yeah, and what you see then in this movie, if I play it again, you see basically how often the system is redoing the mesh adaptation. Yeah, so basically in every time step, it is possible with such a system on structured grid to change the grid dynamically. Yeah, that is one of the strengths of these structured approaches. Okay, turn off the video to be on the safer side. So here we see a typical DNS example from a recent project. So we have a hypersonic boundary layer into which some fluid is injected, and that is then perturbing the boundary layer. Yeah, so we see here the dynamic mesh. Yeah, and here we see basically the fluid here, the cooling fluid, it's nitrogen, how it is injecting into the boundary layer. Yeah, but basically this ability on the structured meshes to use really high order schemes for DNS and LES. And this is also one characteristicum of AMROC. Yeah, so a few words about the general AMROC framework. So it has generally been used quite a lot for DNS and LES. So this is a typical mixing simulation that was done for Department of Energy. We were doing fluid structure coupling problems, like you have seen. So this is a heavy driven problem. So the fracture of a plate by a shock wave in water, a pressure wave in water. And you can also do real fluid structure coupling. So there is an interface to Dyna 3D that is not publicly available because Dyna 3D can't be shared. But here's, for instance, a blast explosion in a building. Yeah, and we see then how the building is kind of deforming, and the mesh, of course, is adapting, and because it's Cartesian, it can be regenerated in parallel very, very quickly. Yeah, so the overall system is about nowadays 500, 600,000 lines of code, but the AMR system is smaller. That is only 50, 60,000 lines, but what makes AMROC so big are all these additional solvers. Yeah, and also many cases. And the version that you can find on the WTF webpage, yeah, the version 2.0 is a little bit older, but you can also already do chemistry with it. But it is a little bit restricted in capability. For instance, as I said, for instance, Dyna 3D, this is an export control program in the United States, and imminently this cannot be shared with the general public. So now let's talk a little bit about combustion. So here I want to introduce combustion first with the governing equations. So the governing equations here to consider are, of course, the reactive Navier-Stokes equations. And I write them down here with a symmetry source term because this is useful to explain the machinery. So 2D with cylinder symmetry source term that then gives us, in addition to the chemistry, a symmetry source term on the right-hand side that we have to consider. And we have viscous fluxes, and we have inviscid fluxes. So here the inviscid fluxes, and then here the viscous fluxes. So, and how do we solve this now? So, of course, it's a full chemistry model. The equation of state is complicated. The heats of capacity are temperature dependent. So in that case, in these explicit solvers, we still have to go through an iteration in temperature in every finite volume cell when we want to evaluate pressure. This is due to this dependency of the heats of capacity and temperature. The heats of capacity come from force order polynomials that come from the Kempkin database. And in AMROC, in the solver, actually the CPs and the enthalpies, they are tabulated, yeah, to save some CPU time. And for the viscous parameters, viscosity, thermal conductivity, diffusivity, they are evaluated with the Kempkin 2 transport library, which can also be quite expensive. And one thing worthwhile noticing, so AMROC often uses, particularly for forward reaction rates, it doesn't use Kempkin directly, but it uses then often for the reaction mechanism a function that is machine generated, and that is actually 2-3 times faster than Kempkin 2 in itself, a small computer science trick. So the numerical methods, they would vary on the inviscid Riemann solver. So, but particularly the row HHL solver is the one that is heavily used. And then we incorporate the viscous terms with central second order finite differences. And important is, of course, the source term treatment. For chemistry, we would be using a splitting approach to incorporate the chemistry. That is typically done with semi-implicit methods of high order, fourth order. And then the symmetry source term that is also incorporated with a splitting approach that is second order. Yeah, but that is worthwhile mentioning. So that's a very capable solver. And quick word about the Riemann solver, because I think this is sometimes underappreciated, how incomplete and still problematic these Riemann solvers even today are. So the Riemann solver that is used here primarily is a row HHL solver. So this is here the bit for the row method. Of course, it has a row average for the temperature. And then here is the average that is used for the heats of capacity. But so the row solver is a very good solver with very low numerical diffusion. But unfortunately, it can become unstable relatively quickly in that sense that it can lead in close to vacuum situation. It can lead to undershoots in pressure and total energy. And what we do here is I evaluate the linear Riemann problem. And if there is an undershoot in density or in energy, the solver would switch to the positivity preserving HHL scheme. That happens only in very few cells, if it happens at all in a computation, but that avoids that the computation is crashing. And then, of course, there needs to be an entropy correction where we use a row solver. And this is a multidimensional entropy correction to prevent carbuncle phenomena. And then there's an additional fix that is correcting the fluxes to ensure that the mass fractions always remain strictly positive. And then even in the second order reconstruction, it is also paid special attention that the mass fractions remain positive. Yeah, and these pieces in the inviscid flux evaluation, these are critical also to, I would say, the success that AMROC is working so well, but it is actually in the inviscid solver, yeah, that where is the robustness. Nowadays, we also have incorporated a mapping approach. And then here, our general finite volume formula is transformed into arbitrary coordinates. And we still solve on the structured grid. And then, of course, we have a transformation matrix T, that is transforming from the computational grid to the physical grid. And then we can still use our normal Riemann solvers in X and Y coordinates. And then this result is transformed backwards with T to the power of -1. Yeah, then again, into the physical space that we are actually working on. And there's a similar decomposition on the viscous fluxes. Of course, on the map mesh, you have to make sure that, of course, you adjust the CFL condition accordingly. Otherwise, the solver wouldn't be stable. You have to consider the change of length scales on the map mesh. So now let me show a few computations that are partially actually a little bit older cellular structure computations, because AMROC has been used quite extensively for that. So when we simulate detonation waves, of course, we know that detonation waves are genuinely unstable in multi-dimensions, and people have devoted a lot of attention to simulating these cellular structures. So what happens is that there is a transverse wave propagating perpendicular to the shock wave of the detonation wave. And there can be multiple of these transverse waves. And when we have the right mixture and the right rectangular cell, the right rectangular detonation tube, these cells can be very regular. Yeah, so what ultimately happens at the cell front is that we have a Mach stem phenomena that is moving up and down dynamically along the front. Yeah, and because this is a very local phenomenon, it is very opportune to concentrate basically all the resolution with matter adaptation at the front to resolve this. Yeah, so here we have a typical 2D computation that is now more than 15 years old, actually. And there you see in the right channel width, so this is hydrogen, oxygen, argon with a Westbrook mechanism. So it is oscillating really very nicely. And you can visualize then, so here we see the mesh adaptation, so it is concentrated at the front. Yeah, and in the back, you don't need a lot of mesh adaptation, hardly any, because this is a really strictly supersonic phenomenon. Yeah, and then one can make suit foils, numerical wise, by basically tracking the maximal vorticity over the mesh, or the maximal thermicity, and it is then producing these really nice detonation cells. Yeah, so that is basically now the situation over the entire duration of the detonation wave visualized in one go. We would initialize these computations, we paint in the 1D ZND profile and then perturb it. So moving on here, so it's a Mach-stem phenomenon, and you can, with AMROC, you can evaluate this quite nicely. And so we would be finding actually two situations in these Mach-stem phenomena. So this would be here a double Mach reflection. And this can be seen because we have a primary triple point and then there's a secondary triple point. And the reflected wave here, the transverse wave, is curved. Yeah, the alternative would be a so-called single Mach reflection situation. People all call this a weak structure, and there you don't have this curved transverse wave. So it is called, in detonation world, it's called the strong structure when we actually have this curvature and the secondary triple point. Yeah, the double Mach reflection situation. Yeah, and with AMROC and now with the embedded boundary method, one thing that I also did about almost 15 years ago is simulate this, for instance, in pipe bands. This is not solving the viscous equation, but the inviscid equation, so with very high resolution. And then when the pipe band there's a significant curvature, what would happen that the detonation decouples. So the shock wave and the reaction front decouples, and then the detonation partially extinguishes in the band and gets reignited by a transverse wave. Yeah, and then this wave gets back and the detonation gets reignited. And then eventually the detonation would continue and come back to the original oscillation in terms of transverse waves. But because of this retonation phenomena, interestingly enough, the largest pressure maximum that you would find in such a computation is not on the outside of the pipe, but actually on the inside of the pipe. Yeah, and here we see some of the adapted mesh. Yeah, so this is the overall phenomena. So if the pipe bend is very modest, the cells basically stay, but they just get altered a little bit. And when then the bend is bending more, we get partial detonation decoupling. So here we get a so-called marginal detonation, and then here actual detonation failure and reignition. But you can see then eventually the detonation would go to the original oscillation. And what is also interesting to see here is that you can see how these triple point tracks, how they have partially shifted their shape. Yeah, when they are becoming very linear and straight, that is indication of the single Mach reflection. And when they are very curved, this is a double Mach reflection phenomenon. Yeah, so here we have these triple point tracks and we have multiple detonation fronts painted over it and an enlargement. Yeah, and in the enlargement, we see that actually due to this transient situation, we have both type of triple points being present in the same simulation and close to one another. Yeah, so here the double Mach reflection structure, and then here the transitional Mach reflection structure. But you can clearly see that the second triple point isn't there next to one where the triple point is there. And this is a nice indication that this is not a numerical phenomenon, but this is actually true physics, what we are seeing. Yeah, and that the resolution is sufficient to capture that. Interesting to see is then, for instance, here this situation when we zoom in. Yeah, so and that is a situation when many of these triple points actually are coming together. And when too many of them are close to one another, there is not enough energy release in the mixture to sustain them all, and then several of them will die out. And when they die out, they also die out as single Mach reflections. And their trajectories become very straight, and then they are fading. So you see they are really fading here, and this is also physics. It's not numerics that they are fading. We can simulate this equally in 3D. Yeah, it's also kind of a computation already also 15, 16 years old now. And what then happens is in 3D is on a rectangular channel, you would be having then situation where Mach reflection and Mach reflection come on top of one another. And this is then a situation here when the front gets very curved. And here then the detonation is particularly locally accelerated. Yeah, when we have Mach reflection together. On the other hand, when we have incident wave together, there the detonation is slowed down more than before. So in 3D, we would have more oscillation along the front. So the oscillation is larger than in 2D. That is happening along the front, but on average, in 2D as in 3D, the whole phenomenon is of course propagating with the original CJ detonation velocity. Yeah, here's a case where we now do this with our new map mesh solver, a new computation by Han Peng, where we do this now in a 90-degree bend tube. Yeah, we see the adaptive mesh and the wave going through. Yeah, so, and this is now done with a new map mesh solver. Yeah, the pipe has the dimensions of 2.5 detonation cells multiplied with 1 to make it kind of tractable. Yeah, and we see then here again, we see the detonation front with these situations, Mach stem, the MI situation, which is a mixed situation, and incident. And when it's going through the bend, many of these triple point lines, they fade out. Yeah, what we get here is we get a complete, for the 90-degree bend, we get a complete decoupling. So the detonation for the majority of the width here is dying out, and this is then getting reinitiated after the bend. Yeah, and so in these experimental images, you see quite nicely that the agreement of this macroscopic phenomenon is really quite nice. Yeah, that's a really nice computation. Now, another computation that we did with our new map mesh solver is this canonical test case of Lear. So in this test case, there was an experiment where projectiles are shot through a reactive mixture of hydrogen and oxygen, and the projectiles are flying with velocities that are all close to the detonation velocity. And so we are getting then shock-induced combustion, a replication of the detonation phenomena on the front of the projectile. Yeah, and because it's replicating detonation behavior, we are also replicating this oscillation with the transverse waves. It is reproduced also in this configuration. And now triple points in this case are initiated at the stagnation point in front of the projectile. And the frequency, how these triple points are generated, is very, very characteristic and very tightly coupled to the velocity of the projectile, to the Mach number. So this is a really sensitive test case. So here in this case, for instance, the experimental frequency is 425 kilohertz, and depending on the finite volume method, this is now the fully viscous solver on a map mesh. If we use the Awesome inviscid scheme, we get 425. If we use rho HHL, we get 430 kilohertz. Yeah. Well, however, what is truly difficult about this whole test cases is to have a setup over the entire range of Mach numbers that Lear actually has carried out experiments. And what we have found is that there is basically no setup that can reproduce all the Mach numbers equally well. And the reason for this is that the chemical reaction model, that is the weakest link here, has a significant influences on these results. So far, there is no chemical reaction model. So we use here the Yachimovsky mechanism that works quite well, but not for all Mach numbers. And so this is basically what we have found, that in these cases, the weakest link is basically the combustion model. So here we see the new solver creating the triple points, and then here the dynamically adapting mesh, yeah, following the triple points. Yeah, so this is working quite nicely. The reason why we really developed this new map mesh solver is because we want to do rotating detonation engines, yeah, like are currently very popular. So here I also want to mention we carried out an RDE experiment in the UK. I supervised this together with Charlie Ryan, and so we built the first RDE experiment in the UK. So it's a very tiny RDE. It uses mass flow rates in total smaller than 10 grams per second. It's running on ethylene and an oxygen, but it is showing the kind of right behavior. So with 9 grams per second, we have about 3 detonation heads or quasi detonations. Yeah, and then with 6.6 grams, we have 2 heads. And with 3.5 grams, we have only one head. Yeah, so we are looking here with a high-speed camera, we are looking into the inside, and you can see the detonation heads. And we also had pressure transducer data, so we are quite confident on what we are seeing. But it's a hard experiment to simulate because it is so small. So all the deficiencies that you would find in a rotating detonation engines, from the friction, from the heat losses, from the mixing, is very pronounced in this experiment. But we are still trying to simulate that. And what we found is if we use pre-mixed injection, so here we now use our new mesh solver with adaptivity. Yeah, and you see the detonation is initiated. Yeah, and then the wave is circling. And of course, you see how, yeah, the mesh adaptation follows the wave quite nicely. Here's from the bottom, we see the ethylene injection. And what we found is, like what many people found in RDE world, is if you have pre-mixed gases already for the injection, you are getting detonation velocities that are always virtually the 7 Joulet velocity. However, in our experiment, we are approximately 40% smaller. Yeah, and this gives indication for all the impurities. And I think it is particularly the mixing between fuel and oxidizer that is to be blamed for these very low velocities actually in the experiment. In order then to have some RDE results that are closer to experiment, we simulated an engine from the Air Force that is running on hydrogen and oxygen, and hydrogen and air. And that has a significantly larger mass flow. So here the mass flow is more than 600 grams, and the deficiency is a lot lower. Yeah, and the injection is done through these, basically through these spherical holes. It's not over the entire plenum. And you can see that this is transitioning then here to 2 detonation waves. This is a truly viscous computation. Yeah, as we can see here, so when the waves are propagating around, you really see that the front stays everything but planar. So we get truly detonation boundary layer interaction already here at the fronts. Yeah, so, and this is clear indication that this is already a viscous computation. And in this case, it was still kind of pre-mixed. We still are predicting something like almost CJ velocity for the detonation speed. And the experiment, because it is larger scale, that is also closer to the Chapman-Joulet velocity. Okay, so I have a little bit time left. So let me give a little bit of an outlook to other high-speed flows that we are doing with AMROC, and particularly the strand mesh approach. So we integrated that into our newest hypersonic solver. So it's a hypersonic solver that is using a 2-temperature model. The previous computations used, of course, a thermal equilibrium assumption, and in hypersonics, you would use thermal non-equilibrium assumptions. Particularly, you want to incorporate the non-equilibrium and the temporal delay that would typically happen in vibration. So here we do this with a 2-temperature model, where we then have an additional energy equation for the vibrational energy. There's a reactive source term, and that reactive source term typically then represents the dissociation reactions. Yeah, so here we have a decomposition of the various degrees of freedom in the gases, and we consider it with a translational temperature and a vibrational temperature. Yeah, so translational rotational temperature is used for translational and rotational degree, and then the vibrational temperature is used for the vibrational degrees as well as the electronic excitation degree. So this is a common approach, and it comes from mutation plus plus that we use here. And then the chemistry gets evaluated ultimately under the assumption that you can combine the 2 temperatures by multiplying them and taking the square root. Yeah, so that is very different to what is done in Chemkin, but it is kind of an accepted model in this world. So this model is after Park, and it is implemented in the mutation plus plus library. But you can guess that if you're making these kind of assumptions, you can't use standard Chemkin to simulate that, because the whole reaction mechanism is kind of differently calibrated, because it's using this funnily combined overall temperature. So we do this now with our new strand mesh solver idea, yeah, where we have boundary layer meshes that are living in a Cartesian background mesh. So how do we grow the strands? So here it is depicted in 3D. Our solver so far is 2D. Yeah, so you would be growing in the normal direction from the surface triangulation. And then, of course, you are growing typical boundary layer cells. What you have to consider is, if you do that, you find that if you just grow in the normal direction and you have corners in your surface mesh, your cells would be of very low quality potentially. So this is nicely depicted here. What you need to incorporate is you need to incorporate some smoothing that the delta X on the boundary layer cells is more intelligently distributed. Yeah, so it is not a straightforward implementation in that sense. And what can also happen is, of course, that you would have clipping phenomena. Yeah, that in this growth phenomena, so that basically the normals can be overlaying, and then you have to clip away some cells, yeah, to make the solver consistent. And that, of course, is one of the reasons these kind of contortions why such a solver in 3D is far from trivial. In 2D, it's a bit easier. So then we have our boundary layer mesh, and that now needs to be embedded into our background mesh. So for the embedding on the Cartesian background mesh, we can, of course, happily use all our level set machinery that we had implemented already before. So from the AMROC perspective, this embedded solver is looking, yeah, like an extended surface, nothing else. So we could reuse a lot of the routines. But then, of course, the two overlaying meshes, they have to communicate, yeah, in the red cells. So you need to exchange boundary information. And for that, then we implemented an additional linear interpolation operation so that we can then interpolate particularly from the new map mesh onto the Cartesian mesh. So let me show some result. So what is popular here is cones in hypersonic flow. These are typical laboratory experiments. So here, for instance, we have a double cone, yeah, a double Mach reflection situation. So, and that is then forming here nice Mach reflection patterns. So this is using the model with dissociation. So we have to zoom in a little bit to see actually the phenomena. So we have our boundary layer mesh near the surface, and then the Cartesian mesh is dynamically adapted. And of course, you want to pick the resolution of the boundary layer mesh outside, similarly to the Cartesian mesh on the finest level, that to make it consistent. And here we see in this picture, we see very nicely the boundary layer, how it gets captured. It's quite important here, of course, for these hypersonic flows. And we see it's a two-temperature model. So here, this is a vibrational temperature. Vibration is always lagging behind considerably temporally in translation rotation. So the vibrational temperature really gets excited only much later. And then similarly, dissociation would take even more time. And so then the nitrogen dissociating, that is very far down in the flow, but it is happening. So this is nice indication for our two-temperature non-equilibrium solver that is necessary for these kind of problems. And so here's comparison between with experimental results and US3D, a very popular hypersonic code. And you could argue that the AMROC results are actually closer slightly to the experiment than US3D, but it's working quite nicely. Okay, so finally, last outlook onto Lattice-Boltzmann methods. So switch of gear here. So AMROC is a strictly explicit system, and we have implemented this Berger-Colella technology, and it seems to be very far away of doing incompressible flows, as you are used to do in OpenFOAM. An alternative of doing that is solving quasi-incompressible, weakly compressible flows with the Lattice-Boltzmann method. The Lattice-Boltzmann method is strictly explicit. It doesn't require implicit iteration, and it works such that it is solving the Boltzmann equation. The Boltzmann equation, which principally is a six-dimensional equation, and in the Lattice-Boltzmann method, this works such that we actually break apart the velocity space into discrete velocity directions. For instance, one stencil that we are using is the D3Q27, where we are discretizing the velocity space in the Boltzmann equation with 27 directions. And these 27 directions are pointing exactly to the next stencil point. Yeah, so, and what you then do is you propagate these density distributions And if you need to evaluate macroscopic quantities, like for instance, density or velocities, you do this by computing the moments, meaning you are summing them all together. And so then you are transporting these quantities, and you are transporting them in the lattice-Boltzmann method always with the speed of sound. Yeah, and that means from one lattice point to the other lattice point. After one transport step, you are doing the collision, and the collision comes from the Maxwell distribution. One computes the deviation to the Maxwell distribution with second order or with third order. This all seems a little bit obscure. We can also evaluate the pressure. The important thing out of all of this is with the lattice-Boltzmann method, one can prove that for vanishing Knudsen numbers, this approximates the weakly compressible Navier-Stokes equations. Yeah, so we are ending up with a solver that is equally approximating the weakly compressible or even incompressible Navier-Stokes equations, but it is strictly explicit and is doing it by explicit operations on a Cartesian grid. And so this solver type perfectly fits what AMROC has been constructed for. And it now gives a perfect opportunity to solve such kind of slow flow problems on the same computational machinery without having to deal with doing incompressible pressure correction iterations with a linear solver as you used to know them in OpenFOAM. Yeah, and then one can also work out how the viscosity and the collision time in this method are connected to one another. And of course, so here is the relation. If we want to then incorporate turbulence modeling, the lattice-Boltzmann method needs this too. This is done then by adding a turbulent eddy viscosity. Yeah, so one needs a turbulence model like in OpenFOAM, and what works easiest with the lattice-Boltzmann method are basically eddy viscosity models where we just have to add the turbulent eddy viscosity to the physical viscosity. What would be a problem is implementing, for instance, Rand's type turbulence models where we have additional transport equations, because we would have to add them to the F in the consistent way. And that is a problem. But LES models, where we can take everything out of the microdistributions on their own, they work very well. So that's what we do. Large eddy simulation, and of course there is mesh adaptation with AMROC, and the whole Berger-Colella machinery is completely unchanged, yeah, with the lattice-Boltzmann method. So this is one special thing in AMROC, that we have implemented adaptive lattice-Boltzmann methods completely consistent with Berger-Colella AMR. The only thing that needs adjustment is this flux correction at the coarse fine boundaries. So how does this work? So in the lattice-Boltzmann method, we have this kind of funny stencil that is also going in diagonals, and we do not have fluxes anymore. Yeah, and we do not have this linear flux formula that we can correct. So, but what we do then for the adaptive method is, okay, we have these distributions that are moving into the fine grid cells, and you see here also this transport in diagonal direction. Yeah, that is different to Cartesian final volume methods. So they are put on the ghost cells of the fine mesh. They get transported in, and you have the collision. And at the same time, distributions are transported out. So that's a combined picture. And now these distributions, they need to go onto the coarser mesh. And this is accomplished basically by coarsening them, and then basically moving them backwards and repeating the lattice-Boltzmann step just on the coarse grid cells. Yeah, so, and that then gives a means of implementing the lattice-Boltzmann method completely consistent also on the hierarchical mesh. And it is a way how it is implemented that is 100% compatible to the Berger-Colella method. Yeah, and I think I was the first one basically putting out the algorithm in this order and make it 100% compatible with Berger-Colella AMR. But that is a big message here, that basically we can do adaptive lattice-Boltzmann, and we do accept this correction at coarse fine boundaries. We do it 100% with the same codes like the finite volume methods. Yeah, and also the lattice-Boltzmann method lives on finite volume discretization, not on finite difference discretization as many people do. But like that, then AMROC is totally unchanged. Yeah, and so here are now a few quick results with the lattice-Boltzmann method. Yeah, so this is, for instance, aeroacoustics over an airfoil, very high resolution, but it's a low Mach number problem. Yeah, Mach number 0.22, Reynolds number 500,000, and it's a typical LES. Yeah, so we see the flow. And then we do a direct aeroacoustic analysis. So we have the microphone here in point P, and we evaluate now the spectral behavior when the airfoil is at 10-degree angle of attack and then at 0 angle degree of attack. And you can see here, yeah, of course, at 10-degree angle of attack, there's a lot more noise at higher frequency than at 0 angle of attack. Yeah, but it works quite well. And the Lattice-Boltzmann method is very attractive for that because it propagates with the speed of sound. So it has the acoustic perturbation included. And because we have this exact transport from lattice point to lattice point, the Lattice-Boltzmann method on the Cartesian grid is also exact when it comes to the advection. So it is a method that has very low numerical dissipation and is extremely good for very high accurate DNS and LES. Yeah, so, and this is also why we used it, for instance, in this project here over porous media. Yeah, so we are evaluating here flow over porous media. And here I just want to show finally some scaling results. So because it's an explicit method, the fastest explicit method that you can imagine in this implementation. So of course we have on the uniform mesh near perfect scaling in AMROC. And then the structured grid solvers with the AMR, what they try to preserve as much of this perfect performance than on the adaptive mesh. But of course, you can see that in scaling, of course, when the adaptation is present, we lose some performance, but it is still rather good. In particular, the Lattice-Boltzmann method, because it is computationally very inefficient, is very hard actually to scale on an adaptive mesh. And so these results here with AMROC, they are quite good, I would say. Okay, so that brings me to the conclusion. So AMROC is designed to provide on-the-fly mesh adaptation for the fastest structured implementation of explicit schemes. The system in itself is in C++, and the discretization that is living on the block, they are in Fortran 77, they are in Fortran 90, or the Lattice-Boltzmann method is completely in C++. Yeah, like also the MHD implementation. And the structured approaches are, of course, very, very good for low dissipation schemes. And the benefit of the adaptation, a factor of 100 in many cases, as you have seen on the slides. But just using structured grids, that is a little bit of a challenge when you have complex boundary layers in arbitrary geometry. And this is where we are nowadays going to the strand mesh approach. So what the strand mesh approach, what I haven't shown you is, we already have a prototype where we are solving implicitly in the wall normal direction. That brings another speed up of 10 for the strand mesh solver. And then, of course, with this strand mesh solver, the future will be then to implement this in 3D. But this will be quite elaborate, and this will be further PhD theses. Okay, so that is the end of my presentation. And I'm happy to take any questions that you might be having.
Okay, thank you very much, Ralf, for your very nice talk. Okay, so in the following, we will move to the Q&A session. So if there is any questions from the panelists, please unmute yourself and discuss with Ralf. So now
there is already one here. Can you say a few words about the availability of AMROC, and it also works on new hardware GPU? So yes. The GPU, of course, for the adaptive solvers is quite a big challenge. You would be assuming that, of course, structured grid solvers with adaptivity have the greatest chances of running on GPU. So if there's any possibility of having truly adaptive methods run on GPU, it would be structured solvers. But we do not have this version yet. I have to admit that our experience with GPU are so far only for Unigrid codes, and I haven't been able to put this very comprehensive project together to move AMROC with full mesh adaptation to GPU, because it will also be, this will be 1 or 2 PhD theses. It is not a small thing to do with mesh adaptation. The availability is, AMROC is available on VTF website, and that is a version that can do all the mesh adaptation with MPI, but it has not included our newest developments like the structured mapped grid on the AMR, and particularly not the strand meshing, because this is still in development. We have basically these 2D versions, but we don't have 3D and so on. And this solver also, because it can do, the solver that I have shown, it can do hypersonic flows on a viscous boundary layer, is not something that can be easily exported to everywhere in the world.
Okay, thank you very much. Yeah. So any other questions from the panelists or audience?
May I ask a question?
Yeah, please.
Yes.
Okay. Ralf, thank you very much for the very comprehensive talk. You mentioned about the interaction with the detonation with the boundary layer within a rotating detonation engines. And I noticed that most of people are simulating rotating detonation engine usually don't consider the viscous. They just use the Euler equations. So my question is, how much is it affected by this kind of boundary layer interaction?
I think
I noticed that the detonation speed doesn't change too much when you consider the boundary layer.
It is, I would assume that we, if Anpeng is in the talk, we had this discussion only yesterday in our own seminar. It might be that if you're not capturing the boundary layer with the required resolution, actually you might be doing more damage to your computation on having viscous boundary condition at the wall. But what we, I think, entirely agree upon is that you need the full viscous model if you have the non-premixed situation. If we have injection of different gases and they are only mixing in the chamber, we truly need to consider the diffusivity, the species diffusivity and the viscosity there. When it comes to the boundary layers, that likely will not have such a great influence. You're correct about that. I think so. I think so.
Okay.
But we need definitely for the non-premixed case. So I have only shown premixed RDE simulations, but for the non-premixed case, which of course is a case that everybody has in their experiments. Yeah. For that one, we definitely need the viscous model.
Okay. So I also noticed that in your experiment, the detonation speed is much lower, like only 70% of the CJ speed. So what's the reason you mentioned? Is that due to the mixing or? I
think we haven't been able to quantify it comprehensively. We are trying to carry out the computations and now trying to mature our computational technology with viscosity and everything to be able to quantify the influence of these various effects. It's my personal opinion that the mixing has the greatest influence. Then possibly the second greatest effect is presumably thermal losses. Yeah, because adiabatic boundary conditions, which have been used so far in the computations, in our computations, presumably are far from satisfied in this case. And then presumably afterwards is presumably viscosity and curvature. Okay. So some RDEs, when the diameter is very small, it will have significant curvature effects, because the detonation permanently might undergo these kind of decoupling phenomena that I had shown with the pipe band. Only when you have a very large radius compared to your detonation cells, I think then you are not having this phenomenon. But I mean, in our case, the diameter is very large, so I think curvature effects are smallish. But I'm thinking that it is mixing, and possibly for this 1 second experiment, that the heat loss might also be quite considerable, because the overall engine has no time to heat up enough that it could be adiabatic.
Okay, thank you very much.
Okay, thank you. So the next.
There's some more questions.
Yeah, go ahead. Yeah, Ralf, go ahead.
Can we use LBM for combustion modeling? Yeah, that is of course the justified question. So the LBM method, the way I have presented it, what you are doing is basically you are approximating the Navier-Stokes equations. The Navier-Stokes equation that are density, total density, momentum, and you are doing this with 27 distributions. In order to add a species, if you do it completely consistently, you would need another 27 different distributions for each species. Yeah, so that would be, of course, extremely inefficient just to get the species in. So what people then have done is, in such scenarios, is if they don't consider complete trivial combustion models that can live with one species only, they have added and combined finite difference equations to the Lattice-Boltzmann method, yeah, to break a little bit with this problem of having so many variables for just the species alone. That is one possibility, but the other problem, of course, is the Lattice-Boltzmann method, like how I have presented it, is for the weakly compressible case, and it doesn't really consider the energy equation correctly. So there is newer work that is trying to develop fully compressible Lattice-Boltzmann methods. But this is much more advanced. And I mean, it would have the benefit that you do not need the separation into viscous and inviscid fluxes. The Lattice-Boltzmann method is viscous by definition, but this is not so advanced. So the short answer is you can use LBM easily for combustion modeling, let's say for a low Mach number situation in the quasi-incompressible case, when you use a very simple one species reaction model. Yeah, for very slow reactions, like let's say surface reaction in the grounds, you can use LBM and people are doing it. For truly sophisticated combustion modeling, like I presented in the first part of the talk, it is quite challenging. It is quite challenging. So the question how we would incorporate temperature-dependent heats of capacity into the Lattice-Boltzmann method, I'm not sure that anybody has answered this question. I think it possibly can be done, but the modeling it would be very challenging. So this is why we are pursuing basically both avenues. When I just want to do standard combustion, I just stay with the normal finite volume methods that work so beautifully. That would be my answer.
Okay, thanks. So we have another question from Dr. Li Xiangpeng. So
can we combine SMR and OpenFOAM? Well, the technology is very orthogonal. So when we talk about OpenFOAM and the normal structured AMR, when we are looking into the details, we are finding that virtually everything is orthogonal to one another. That is starting out already basically with the basic data structures. So in structured AMR, we have Riemann solver problems, and we want to have the entire state vector living close together. That because when we evaluate the fluxes at the boundary between a cell, we need left and right state, and we need the full state vector. In OpenFOAM, I think by default, you are storing various scalar fields. Yeah, and the scalar fields are fully separated because it is intended for segregated methods. Yeah, where you are iterating independently over the scalar fields. So already our basic data structures are completely incompatible with one another. Then, of course, I think then also in incorporating the SAMR, I think the problem kind of is at the moment that you start incorporating true structured mesh adaptation, the full Berger-Colella, like we are doing it into OpenFOAM, virtually the entire meshing machinery inside almost goes away. Yeah, and then can you still make it compatible the way how you have implemented the fluxes? Possibly, but you presumably also would lose a lot of performance. Yeah, so I think what you are asking is, people presumably want to have the same interface like OpenFOAM, that it looks like a standard OpenFOAM solver, but underneath it would be just pulling out the majority of libraries. Yeah, so it is a quite complex task, presumably, what you are asking for. Yeah, it is setting aside all the implicit solver machinery in OpenFOAM and replacing the entire meshing machinery with its own approach. And so, yes, I think it's a challenging question, and merging them together might be very challenging. So I think the moment that you AMROC is mature, AMRX would be mature, Boxlip would be mature. The moment that you try merging them into OpenFOAM, you find that nothing really fits together.
Okay, okay, thank you very much. So can I ask you one more question?
Sure.
Yeah, so normally, when we use AMR, we will always have the load balancing issue. So I'm not sure
right.
how this is resolved in AMROC.
It's as you saw, we are using the space filling curve technology, and it has certain limitations. You need to understand in AMROC how the load balancer fits together with a distribution strategy. So the moment that we project the workload down on level 0 to have a relatively simple and fast distribution problem, we should not create too much load imbalances on level 0. So the moment that you have a level 0 mesh that is consisting, let's say, only by 4 by 4 cells, yeah, then you have only 16 elements. you could only distribute to 16 cores. Yeah, if you then create 20 levels on top of it, the partitioning would be terrible. But so you have to understand, okay, I can only use, let's say, 4 or 5 levels, have a more refined base grid level, and then I have more units available for all the cores that I have available. The moment that you understand this, AMROC works very well, but it cannot do any magic. So I think with every AMR system, there is no magic. I think this is intrinsic to all the AMR libraries, let it be BoxLib or AMRX or AMROC. You need to understand how it is internally implemented and what the parameters are doing. If you just rely on it to do its own magic, the parallel problem might be solved rather poorly. So you might be losing a lot of performance.
Okay, thank you.
But in order basically for the user to gauge this, the AMROC computations typically print after each run. They do kind of a printout. So the user sees if what you want, of course, is that the compute performance goes into the finite volume method or the Lattice-Boltzmann method. And AMROC would always give you, at the end, it would give you a relatively detailed printout where all the time has, so it's benchmarking itself while it is running. And so that then gives the user indication if something is wrong. Or if you would be exercising the space filling curve way too frequently, that can also happen in some cases when the user chooses very naive settings. You can also lose time there, but the code would tell you at the end, and if this is nicely analyzed and then you act according on, then it is possible to adjust it properly.
Okay, thank you very much. So another question is for your IDE case, I think it's in slide 13. So for that one, I think it's a non-premix or it's a premix case.
These here are all premixed for the time being. For the time being, they have all been
with discrete inlets, right?
Say again?
Premixed, but the inlets actually are not continuous, right?
Yes, they are spherical. We also have non-premixed computations now, but I wasn't able to include it for the time being.
Okay. Yeah. Okay.
But it's premixed. It's still kind of a demo computation.
Okay, because you mentioned mixing is probably one of the factor for the.
Absolutely. We have indication of that. It's only I have these results. This is Han Peng's latest work.
Okay. Okay.
You cannot have everything. It's
yes.
Yeah, no, and have a complete RDE. It's I think let's say in 6 to 12 months, I think we should have very sophisticated computations also with non-premixing and a high maturity on this kind of cases.
Ralf, we can't hear you now. Double sum. So I think we can turn off the video probably better.
Yep.
Yeah. So okay, thank you very much for answering my question. So there is another one from Prof. Zhicheng. So you can see it from the chat, right? Hello, Ralf.
Oh, okay. I see.
Yeah.
Have you any comment on OpenFOAM AMR engine regarding the flux interpolation? No, I do not have any comments about that, but I can, because I do not know the details, but of course, this is a crucial situation. So usually it's the refluxing business across fine interfaces is, of course, with all these adaptive solvers that use hierarchical meshes, this is where it becomes mathematically tricky. And you can run computations very happily entirely without the refluxing. So the results usually will differ very, very marginally. Yeah, for instance, in the most chemistry cases, we might also not even run with a flux correction. It is when you do very sophisticated error analysis and you really measure the second order or higher order of your scheme that the flux interpolation really makes a difference. But because it is like that, the flux interpolation just with the eyeball norm cannot be determined very easily, that gives people implementing solvers a lot of leeway. And this is why this is a component, that might be quite incorrect in many solvers, and most users wouldn't even see it. And I can tell you, this is one of the bits, of course, the moment that you evaluate and assess a solver thoroughly, and you do comprehensive error and order analysis, this is when you see the missing and the mistakes in such kind of components. I can imagine that it is full of errors potentially, but I do not have any direct comment on OpenFOAM, but it is very, very common. We often find in collaborative projects when people have other solvers that there are mistakes in these kind of components, particularly also the temporal interpolation and so on. So it is very easy to have lots of errors in these components. But the good news is you can still do mesh adaptation and completely forget about the flux correction, and you can run slightly non-conservative. And usually if you place your adaptation in the right areas, the influence on the result is very smallish. That is kind of the good news. Yeah, so all the users who are telling you this isn't a problem at all for me, they are kind of right. It's only when you really look really hard and you do really difficult problems where the mesh adaptation needs to go really into the features. And the coarse fine interfaces are really across, let's say, turbulent interfaces and so on. This is when you see the mistakes.
Okay, thank you very much. Another question is about, so there is another question in the chat. So Ralf, can you see, or I'll read it for you?
Okay. Yeah. No. So the business with GPU. I think we can. I think when you talk about GPU and mesh adaptation, so the GPU is good for number crunching. So I think if we have a hierarchical mesh and we know how to distribute it well to all our GPUs, we can move all that data into the GPU and we can compute very efficiently. The problems, of course, however, arise if we have to redo remeshing and we have to reorganize our entire hierarchy. The GPU would be terrible for reorganizing the hierarchy. The GPU is terrible for doing all these copy and integer operations. And it is a complete different type of parallelization than sweeping over the mesh if we have to reorganize our data. So the problem is more when you want to do AMR with GPUs. I think you will very likely end up with a code that is doing all the mesh adaptation business on the GPU and is then copying in the data on the GPU for the update sweeps. But of course, then when you redo the mesh, you have to copy it out, you have to reorganize, you have to copy in. And so then when you do AMR very frequently, we all know that the memory access to GPU is very slow. Yeah, so then it can easily happen, I think, if you are not careful and you want to do lots of AMR, that only the memory copy in, copy out of the GPU is more expensive than actually what the GPU can give you on performance. So I think you will have to end up with a system, I guess, that is doing very few AMR as a first approach, very rare mesh adaptation, and leaves all the data as long as possible on the GPU, that it only does the update sweeps, but no reorganization of the data. Yeah, so, and I think this is really what the problems are. And I'm not sure that somebody has really comprehensively solved this, but that would be one of the key issues that you have to accept. So I showed you cases where we have lots of mesh reorganization on very smallish meshes. I think you have to give up on this idea on the GPU. We would be using very large blocks that we change very rarely and throw them onto the GPU and keep them there as long as possible.
Okay, thank you very much. Okay, so may I ask you one more question? So
sure.
Now, currently, what is the capability of AMROC framework to like modeling detonation or supersonic combustion via detailed chemistry for for hydrocarbon fuels?
Basically, like anybody else's system. You can set up the solver effectively for arbitrary large reaction mechanisms.
Okay.
So the way how AMROC is constructed is that the codes are kind of individually compiled. So it would always be using a state vector through a template parameter that is optimal for your setting. Okay. Yeah, so you can basically you can use the codes as optimal as possible. That is one reason why I on the complex chemistry, I prefer to collaborate with people directly, because the complex chemistry code has a lot of setup options in Fortran and in C++ to run kind of optimally. But principally speaking, the short answer is it can do arbitrary hydrocarbons, can do everything that Chemkin can do.
Okay.
But of course, the moment that your mechanism gets gigantic, for 3D, you better want to use a reduced mechanism.
Yes. Okay. Yeah. Thank you very much. Okay. Any other questions from the audience and from the panelists? Okay. Thank you very much for the very nice talk, Ralf. Okay. So all the panelists, turn on the camera and join me thanking Ralf again. Okay, thank you very much.
Thank you.
Can I actually see everybody?
Yeah. Okay.
Yeah.